please feel free to unmute yourself and ask any questions. Danylo, please share your screen and start whenever you're ready.
Okay. Okay, so today is going to be, well, in this last lecture, I'm going to talk about the universal optimality proof for the E8 lattice and for the Leech lattice. So I first want to discuss some topics which don't have directly a relation to that result, but which are, in the sense, they kind of make an appearance when you try to prove it. So I want, and these two topics are purely about modular forms. So I think it's a good opportunity to discuss them. So let's look back at the Eisenstein series of weight 2. So if you remember, it's given by this Q series. So it's a generating, more or less, it's a generating function for the sigma, for the divisor sum function, plus this -1/24 as a constant term to make it modular. Well, okay, to make it not quite modular. So the thing with the Eisenstein series of weight 2 is that it's not modular, but it's really close. And while at first it may appear like as an annoyance, so you can't apply most of the results we learned, but actually it's in a sense a feature. So it kind of points to some interesting generalizations of modular forms, and we'll talk about two of them. There's certainly more ways of generalizing this behavior. So first is, well, let's look at one question that I haven't mentioned almost anything about what happens when you differentiate modular forms. And there's actually quite a deep theory there. But on a very basic level, there's something which you can do very easily using the Eisenstein series of weight 2. So let's look at this differential operator. So there's some normalization constant here to make it preserve the rationality of the Q expansion. So D is just you either differentiate in tau, but then you have to renormalize it, or it's the I think what's usually called the Euler differential operator in Q expansion. So what it does actually, it multiplies the Q to the I by its degree. So, well, if we just look at what, well, let's say we have a modular form of weight K, and let's apply this operator to it. So simple calculation shows that the modular transformation property breaks down, but it, in some cases, it still works. So what happens if you differentiate the modular transformation law? I mean, one thing is fine when you evaluate, when you apply D to the f of gamma tau, you kind of pick up this automorphy factor. But on the right-hand side, where you already have this automorphy factor, you have to differentiate it as well, and then you pick up this term. And it kind of spoils the modularity in all cases except when the weight was 0, which is, I mean, this case makes perfect sense, because if you differentiate a modular function, you get a modular form of weight 2. So I haven't quite mentioned why this makes sense. So the reason is modular forms of weight 2 are in a very, I mean, in the setting of this modular curve. So when you take the quotient of the upper half plane by the group, then the modular forms of weight 2 correspond to invariant differentials on the modular curve with simple pole at the cusp, or at the cusps if the curve has more cusp than one. Okay, so it's kind of a side remark. So and you don't have to worry if you don't fully understand what I just said. So what I want to say is the case when K is equal to 0, it's kind of very easy to see why it should be the case even without differentiating anything. But well, if you look at the previous slide, this factor over here, c tau plus d to the power -1, well, or to the power +1, but I mean, it depends on whether you put the automorphy factor on one side or on the other. So it appeared in the transformation for E2, and because of that, if you now take, well, this differential and you subtract this combination, I mean, the product of E2 and F, it actually deals with this factor. So, and then it's easy to show that this combination again satisfies the modular transformation law. So it is a modular form of weight K plus 2. And this is called the Serre derivative. So, I mean, I'm not going to say much about it except, well, it depends on K, but I kind of suppress it from notation. So one cool thing that one can do using Serre's derivative is that, well, we can look at these Eisenstein series that we have, and let's see what happens if you differentiate it. So for E4 and E6, because of this, well, because of the fact that Serre derivative sends a modular form of weight k to modular form of weight k plus 2, so you can work out that it exactly means that if you if you differentiate E4 and you subtract this bit, which comes from the Serre derivative, you should get a modular form of weight 6. And some simple calculation shows that it has to be this. So it has to be E6 minus E6 over 3. And similarly for E6, so it's just an application of the Serre derivative. But for E2, it's a separate calculation that you do that actually. If you look at d of E2 minus E2 square over 12, then it satisfies modular transformation properties in weight 4. So again, this gives you this formula. So altogether, if we think about it a little bit, it tells you that whenever you have a polynomial in E2, E4, and E6, you can differentiate it. So if you want, you can do this as an exercise, but I more or less explained how to do it. And you can again get a polynomial in E2, E4, and E6. So, so what this means is that, well, if you define just formally this space, so M tilde star of gamma 1 to be the ring of polynomials in the 3 Eisenstein series E2, E4, and E6, then it is closed under differentiation. Well, okay, so let's just formally call this a quasi-modular form. So we will call an element of this ring a quasi-modular form. It's not a very enlightening definition, and one might ask, well, is there a more kind of meaningful description of this ring? So we just said, well, these are polynomials with modular coefficients in E2, but can we, like, if one meets an object in nature, can we actually understand conceptually what it means for it to be a quasi-modular form? So we can, of course, always work it out, find if it is or not, but can we give some natural property which describes it? And actually, it turns out that there is one. Well, there are several ways of defining what it is, but one of the easiest to state is, well, there's a certain parameter to this quasi-modular form, which is called the depth. So if the depth of the quasi-modular form is 0, then it's just a modular form. And they get increasingly more complicated as the depth increases. But on a naive level that I said before, the depth is just the degree of the polynomial in the E2, in the weight 2 Eisenstein series. So yeah, so the description, the intrinsic description of quasi-modular forms is just, instead, we just require, again, we're talking about holomorphic functions on the upper half plane, but instead of the modular transformation law, where we said that if we slash it in weight k with gamma, we again get f. In this case, when we slash f with gamma in weight k, we get some polynomial in this vector here. So if you look a little bit more carefully at the transformation law for E2, this is exactly the same thing that appears there. So kind of we allow, as we allow products of E2, we also have to allow like higher powers of this term. And one can show that this definition coincides with the naive definition of polynomials in E2 with modular coefficients. Well, I'm only talking about this group, PSL2Z. So they were introduced by Kaneko and Zagir in connection to a certain problem about counting maps between curves of different genera. But it's completely, in a sense, it's a completely separate topic from that. And they actually, this is not their original definition. They studied something that is now called almost modular forms, which is, again, slightly different thing. So instead of requiring certain complicated transformation laws for a function which is still holomorphic, we now take a function which is not quite holomorphic, but it has a simple behavior. simple non-holomorphic behavior. But then the transformation law requires the same as for usual modular forms. And so in this case, it has to be, so we require it to be a function of tau, which is a polynomial in 1 over y with holomorphic coefficients. And then we require the transformation law, the same transformation law as for modular forms. And one can show actually, so with this notation I have on the slide, unless I made a terrible mistake, so there is a correspondence between these two objects, and it exactly sends fj to fj. So if you have a quasi-modular form in this sense, and you just take this vector of function, holomorphic functions fj's, and you form this object, then it is an almost modular form. Okay. So any questions so far? Okay, so now one could wonder whether whether the quasi-modular forms appear somehow naturally in some problems, and well, the answer is going to be yes, because they will appear naturally in the solution of the sphere. They have appeared naturally in the solution of the sphere packing problem by Vezovska, but also they appear again in the proof of universal optimality. And unfortunately, we don't really have a good conceptual reason why they appear, but there is kind of there is a reason. So once we have did certain computations, one can figure out that in hindsight, this was a computation about which involved quasi-modular forms. So let me just clarify this a little bit, and this is a nice thing. So one can meet quasi-modular forms in a very natural setting if one works with vector-valued modular forms. So I haven't quite talked about that, but you can imagine the definition is not very hard to give. So instead of working with functions with values in C, so we replace C by a complex vector space, which has which carries the representations of the group gamma in question. So in our case, it's going to be PSL to Z, or actually SL to Z. There's some difference there. And instead, now again, I mean, the slash operator I have defined for scalar functions, but we can just verbatim carry it over to vector valued functions, which is you apply the slash operator to each component individually. And now the modular transformation behavior that we want is that the slash action on functions, on the vector valued functions, should correspond to the action of the representation that we're given. And if you take n to be 1 and the representation to be trivial, you recover the scalar valued case. So what happens is, well, there is a very natural representation if you look at the group SL2Z. Well, if you look at the group SL2R, but of course, if you restrict, you also get it for SL2Z. And that is the symmetric power representation. And what happens if we just, I won't say anything, almost anything about the theory of vector valued modular forms, except in this case. And this is a nice result by Kaneko and Nagatomo, who, by the way, for the reason I'm not quite sure, I'm not sure why exactly they needed this statement, but they were interested in vertex operator algebras. So it kind of gives a connection maybe to what Henry is going to talk about. So in any case, the result is if you study vector valued modular forms for the symmetric power representation of SL2Z, then there is a simple linear transformation between these objects and quasi-modular forms of weight. Well, of certain weight. I mean, it's all written here. And this is a completely explicit thing. You can go both ways. Here you have to require some additional conditions for these forms to work, for this to define a symmetric power representation. But in this direction, it always works. And just in case you don't know or don't remember, well, there's some choice in which you can, there's some freedom of choice in how to define it. But if you do, like on the level of matrices, you can use this definition. So you just write out these polynomials of degree n, write them out in the basis, and then you collect the coefficients, and that would be your matrix rho of gamma. Okay. So, well, this is kind of, it might seem unrelated to what I'm going to talk about next. So there's another topic purely in modular forms, which I want to cover before I move on to the sphere packing problem and the universal optimality problem. So let's look back again at the weight 2 Eisenstein series and look back at, look at its transformation law. So what we can do? Well, we can rewrite it in a way using the slash operator. So if we divide both sides by theta plus d squared, then we get something on the left, and rearrange terms. We get something on the left, which is, well, the value of the function minus the action of the slash operator on it. So if it were modular forms, then the right-hand side would just be 0, but it is not. So, well, we can rewrite it in symbolic terms as follows. So we have G2 minus G2 slash gamma is equal to some function phi of gamma, which is this. And well, we can ask first, well, what kind of function? So this is not a single function, it's actually a family of functions. So it depends on tau and on the matrix in SL to Z. So we can ask, well, can we get arbitrary families of functions in this way? Well, the answer is actually no. And it's something very simple. Of course, if you've ever had anything to do with first cohomology group, you probably already know what I'm talking about. But in case you didn't, you never had a chance, then on a very basic level, what you do is, well, we want to study how this family of functions behaves. And it satisfies a simple property. So if you take, well, this function, which is I called phi gamma 1, gamma 2, you can rewrite it by adding a term and subtracting it again as a sum of two terms, which are again of the same form, except one of them you have to also add the action by the second group element. So what I'm trying to say is this formula. So whenever you have two elements in the group, gamma 1 and gamma 2, then the family of functions phi should satisfy this kind of what is usually called the crossed homomorphism property. So you kind of twist the second. If your action were trivial, it would just be the phi sends the product of gamma 1 and gamma 2 to the sum, but the action is not trivial, so we actually twist it by one of the terms, but by one of the two group elements. So this is what is called the one cocycle for the group PSL to Z. And then the question, well, the one that I kind of implicitly formulated is, well, what kind of functions can we get if we try to solve this equation? So we already know that if we have such family of equations parameterized by an element of PSL to Z, the right-hand side should be one cocycle. But let's say we're given a one cocycle and we want to find a function f such that it solves it. So this, in homological terms, it just says that the one cocycle is trivial and we want to find the pre-image of it under the coboundary map. Okay, and there's some requirements. So if you want to have some nice theory, you have to require some properties of these functions. So somehow analytically, it's very nice to have all functions to have at most polynomial growth at the boundary. And again, I didn't quite define it before what this means, but you just imagine that it doesn't blow up, doesn't have like poles anywhere at the boundary in a sense, or essential singularities. So one kind of situation in which one can meet these types of generalized. Okay, I forgot to say one thing. So if this cocycle is trivial, so if all these functions are 0, then we're talking again about modular forms. So kind of modular forms are a special case of a modular function. And in a sense, it's the homogeneous space corresponding to it. So whenever you try to solve this equation, you can always add a modular form and it doesn't change anything. So it's kind of, the solutions are already well-defined modular spaces of modular forms. So there's one very nice construction that leads to very deep theory of such objects. And it's based on a very strange thing. So there's a completely elementary identity which if you apply it in a good way, it gives you kind of a lot of very non-trivial results. And the elementary identity is the following. So if you have any smooth function on the upper half plane and you differentiate it k-1 times, and then you apply the slash operator in weight k, then it's actually the same as applying the slash operator in different weight, in weight 2 minus k, and then differentiating. So this k minus first derivative intertwines the slash actions in weights k and 2 minus k. I mean, it's not very hard to prove. Well, one thing that may be more familiar, if you take k to be 2, then the identity is just saying, well, if you differentiate the function where you substitute, so this would be weight 0, so this would be just f of gamma tau. And then this identity is just the chain rule for differentiation. So, but there's something funny about this exact number of times you have to apply the differentiation operator. So if you don't do it in the correct way, the formula gets much more complicated. And as a corollary, so if you look at this identity, let's say that this right-hand side, so the function under the slash operator that we have is actually a modular form. Then because of this, the fact that it's a modular form, we would know that it's fixed by the slash operation, the slash operator in weight k. But now let's look on the left-hand side. So now f is the k minus first primitive of the modular form of weight k, and the identity is saying that if you take the action in weight 2 minus k on f and we differentiate it k-1 times, then we actually recover, we get the same thing as if we didn't apply anything. So if you differentiate, okay, sorry, what I'm saying is kind of a bit awkward. So if you take gamma and we take identity, and then we subtract these two identities. So we do it for gamma and for the identity of the group, and we subtract them. Because of the fact that this is a modular form, this will be 0. And then what this identity is saying is that the thing inside the differentiation, so f slash 2 minus k gamma minus f, has to be a polynomial of degree at most k minus 2. Because when you apply k minus first derivative, you get 0. So it's I don't want to spend too much time on this, even though it's a very interesting topic. I'll just give one example. And there will be, so I'm not just talking about this because it's nice. I'm talking about this because, in fact, when we try to make the Fourier interpolation formula for the universal optimality proof, we do meet such objects when we try to solve certain modular equations. So one example is you can look at the Eichler integral of E4, and by Eichler integral I just mean this, the third primitive in this case. So you write down explicitly this expansion, but then what I want to say is that if you apply d cubed to it, you just get E4. So this is just, I took the primitive already. And then the Bohl's identity, it says, well, if you take this thing, well, we can compute it directly because the Q expansion was periodic. So you only have to do translation of the polynomial by 1 and subtract. So you get the polynomial automatically. But if you look at the S, the action of S in weight -2, then Bohl's identity tells you that if you differentiate this thing 3 times, you should get 0. So it tells you that you should get a polynomial. It doesn't really tell you which polynomial, but one can work it out. And it's actually this polynomial. And you see you get a zeta 3 appearing in it, which is, yeah, it's nice. So, and I'll come back to it a bit later when it actually appears in the proof of the Fourier interpolation formula. So, okay, sorry, one more thing is, it's actually not completely trivial to verify that these two functions, so this would be psi t, and this would be psi s, if you kind of generate a cocycle using these two functions, there are certain requirements it has to satisfy. And a priori, it's not clear why these polynomials do that. So if you try to see, you give yourself two polynomials, and then you try to see if they define a cocycle as some non-trivial relation, which actually these polynomials do satisfy. And that's part of the Eichler-Shimura-Manin theory that I'm not really going to talk about. Okay, so now let's go to the topic that probably more people are interested in. So we're talking about magic functions for sphere packing. Well, in a moment I will also start talking about universal optimality. But first, for sphere packing, I'll just remind. So Kohn and Elkis have found that using their linear programming bound, that if one could construct a function, which I'm not sure at which point they started calling magic function, but it certainly is. So if one can construct a function with these three properties, so a function which is radial, which has value 1 at the origin, and satisfies the inequalities given here. So it has to be positive semi-definite, I guess, or positive definite in the sense that the Fourier transform is non-negative, and the values of the function itself should be negative, well, or non-positive once you go outside the radius square root 2 sphere. So if you could find such a function, then you would prove that the E8 lattice is the optimal sphere packing in 8 dimensions. And I mean, assuming that this is the radial component of this function, then from the way they prove this, they actually obtain more information about it. And exactly what they're saying is, I might be missing one of the conditions, but it doesn't really matter. So it has to vanish at these lengths square root 2n, and actually to the second order for most of them. And the same property should also hold for the Fourier transform. I guess I'm abusing the notation very badly here, but what I mean here is the function, the radial component of the Fourier transform of f. Okay, so of course you all know how this story ended. So Wiazowska has found a beautiful construction of such a function using Laplace transforms of weakly holomorphic quasi-modular forms. And jumping ahead, at some point in the talk, I will actually explain why, in hindsight, quasi-modular forms should have appeared. So, and then the proof, well, the theorem was actually because of the previous theorem by Kohn and Elkis, she also obtained the fact that the E8 lattice is the optimal sphere packing R8. And shortly after that, of course, we found the same function, using the same strategy. Sorry, not the same function. Analogous function in dimension 24. Again, as a Laplace transform of a weakly holomorphic quasi-modular form. I'm kind of lying a little bit. It's not exactly Laplace transform of a weakly holomorphic quasi-modular form. One has to do something to it, but it's kind of, I don't want to go into that kind of details. And one also has to multiply it by sine squared of pi x squared over 2. I hope, yeah, that's what it is. Okay. So, and then in the universal optimality problem, one has to satisfy similar constraints. Oops. Yeah, constraints similar to these, except now that we have kind of general potential functions we have to match. It turns out that the values of f at square root n and f prime at square root n are more or less arbitrary. Well, they depend on the function, but there's no obvious restriction we can impose that would simplify our life. While on the Fourier side, they would have to vanish again to the second order. So, and because of the certain duality between this problem and the problem for the Fourier transform, it really doesn't help us much that we only impose conditions on one side, because if you can solve this problem, we could also solve it for the dual. So if you could find the function which prescribes about these values, we could also do it for the Fourier transform, and then it will become the full function, the full problem of prescribing, giving some values for all these 4 sequences of numbers, how to find a function. But in the end, well, this is exactly the result that is true, that it's related to what Henry was talking about yesterday, that somehow, well, we're not very good at satisfying the inequality part of the LP bound, but we're very good at solving equalities, so it seems, especially in the polynomial case, where it's kind of trivial to find a polynomial with given zeros. And then in the Euclidean case, it turns out to be very non-trivial to find a function with given zeros on the function and the Fourier side. But in the end, this is somehow very precise a matching of what one needed to what actually is possible. So, and what happens is precisely the best result one can hope for, is that when whatever sequences of numbers you prescribe for these values of f prime and the Fourier transform and the derivative of that at square root 2n, you can always find, as long as they have some certain decay properties, you can always find a unique function. And not only that, it also there are some finitely many points that you can omit. And these are exactly the finitely many points that we don't care about, because the lattice starts at a certain point and it exactly matches that. So there is some kind of a miracle that such an analytic result holds precisely for the, I mean, with the data that we have from the sphere, from the LP bound. And I have absolutely no idea why this is the case. But now the rest of the talk, which is, I think, about 15 minutes, I will spend trying to explain why this is, why this problem has anything to do with modular forms, and how one could in principle approach it. So what we did in the paper is maybe a little bit hard to follow, and it certainly is not a very short argument. But what I will do in this talk, I will cheat a little bit, and I will try to kind of give an idea of I will give certain simplifications of this problem that suggest that really the solution should involve modular forms, and then I will explain why it also involves these kind of generalized modular objects. So exactly which types of quasi-modular forms and which types of Eichler integrals should appear. And I won't give a precise reason why everything works in the end, and I actually don't have a good idea why it does. But once you go through all the details, everything matches perfectly. So, and of course, our motivation so this is, maybe I should mention, so CKM RV, really only R should be with an initial. So this is a theorem by Henry, Abhinav, Steve, and Marina, and myself. And our motivation, of course, was the universal optimality of the reach and the E8 lattice. So, okay, so now what can we do? So first, the question is how the modular forms appear, or at least how to see SL2Z in this problem. And that is actually not so hard to see. And I don't know, I kind of like to think about this problem as a self-proving conjecture. So I think at the point where Marina formulated it, it seems like a very unlikely statement to be true. And even if it is likely to be true, certainly such a thing would be studied by someone before that. But in any case, if you try to play around with this conjecture, you just believe that this is the case, that such a formula does exist, and you try to, well, either prove or disprove it. And one of the, well, I'm not sure if it's necessarily the gut reflex of many people, but one thing which you do with such an identity is you try to plug in something for f, and hopefully something which plays nicely with the terms on the left and on the right. But of course, it was not at all trivial. So I don't want to go too much into history of how Marina solved the sphere breaking problem, because it's, well, she herself talked about it many times. But so the nice thing, I will still reiterate how one sees modular forms in this picture. So we want to verify this identity for all Schwarz functions. Well, let's pick some Schwarz functions which we know how behave very well. And in most cases, this means the Gaussian. So if you look at the Gaussian, and we pick a complex parameter tau, which turns out to be very important. So if you look only at the real Gaussians, it's a bit harder to see kind of the modularity entering. So then we know what the Fourier transform is. So we actually know all the terms in this identity. And then it looks like a very strange identity relating the values. Well, if you now look at this identity in terms of the parameter tau, it looks a bit strange, but it already hints at something modular happening. So what happens is the identity can be written in this form, where I have introduced some shorthand notations. And you don't really have to think too much about what is going on inside this sum, because it has two very simple properties. So first, it's almost like a Fourier expansion of something. So it wants to be periodic. Well, not quite, because there's also a linear part here. And the coefficients are the functions that we have assumed exist from this conjectural interpolation form. But we also, again, we don't want to think about them at all. We kind of want to put everything in this black box. And then, well, what we want to keep in mind is the behavior of this function in tau. So the generic behavior of this function is in tau. If you didn't have this term, it would be just periodicity. But because of this term, we have to apply periodicity twice. So we have to take the second discrete difference. And that's exactly what's happening. Well, I'm not sure if you have some, is it visible what's going on below this line, but hopefully you do.
Yeah, I can see that.
Okay. So, so the condition becomes, well, if you apply second difference to f, then it should be 0. And if you apply second difference to g, it should be 0. And of course, well, in general, this doesn't necessarily imply the expansion of this type with only non-negative coefficients. But if we impose additionally some growth condition on f and g at infinity, then it does. And it's a simple kind of modification of the argument with Laurent expansions, if you will. So, but I don't want to spend too much time on that. So what happened is, well, the problem, this conjecture, which is self-proving. Well, I don't want to say it's self-proving because it's only up to a certain point it's self-proving. After a certain point, it becomes very difficult. But to an extent, it's self-hinting. Maybe it's a better word. So we have now three conditions. So one of them is the important part is the interpolation formula that we started with, and the other two tell us the shape of the functions in this equation. And now it's kind of nice because in a sense we can forget everything about the Fourier analysis and just study this problem and complex problem about functions of complex variable on the upper half plane. And it does look somewhat similar to modular forms because we have the same type of T and S relations, except, well, it's not directly a modular form yet. So what one has to do is a nice trick, which I've learned from Marina. So what you do is you kind of, well, you have these relations you can rewrite using Zesh operator as relations coming from the group ring. And then, well, what you can do, well, you don't really know what kind of relations follow from these two. So you just try, well, are there any relations between f and f/t? Well, it doesn't look like it because you only have a relation involving f, ft, and ft squared. So let's add it to a list of things which you can't decide. Then you add, well, let's add f/s. Well, f/s is g, and g is kind of one of the two functions. So let's add it to the list, and let's not add f/s. And then you iteratively try to do this thing a couple more times, and by trial and error, you figure out that, of course, there's a more intelligent way of doing it, but if you kind of approach it naively, you can do it just by computing. And you figure out that, well, once you reach this vector, or there are some other choices of 6 functions that you can pick, then everything else, it turns out you can actually express in terms of these 6. So what this means is that this 6-dimensional vector space of functions on the upper half plane is stable under the action of PSL to Z. And whenever you have this situation, it's very natural to consider it as a vector valued modular form. And this is exactly what happens. And the conditions become this vector. I'm not sure. Maybe I should actually put a transposed here, the way I write it. So this should be a column vector. So what happens now? the type of modular forms is now more complicated. So we're talking about vector valued modular forms with some representation, but the conditions become now the same conditions we've seen for the scalar valued modular forms. So the functional equations now, well, if you ignore the right-hand side, is just saying that this is a vector valued modular form. But you remember from previously in the lecture, I've introduced the notion of modular integrals, and that's exactly what it required. So in the definition of modular integrals, I required an identity for all elements of the group, but actually it's enough to require it just for the generators. So what this system of equations so these are equations for vector valued modular integral for PSL to Z. For a certain representation which is given by these two matrices, and I will show to you what they look like. And these cocycles again are given by certain. Okay, I think I should say what phi is. Phi is the Gaussian. So phi is e to the I pi tau x squared. And then these are explicitly the parameters that occur in this functional equation on the previous slide. So it looks kind of complicated. And there's something, again, here, which I don't immediately see from the derivation of this problem that it should be the case. And that is, well, whenever you just specify a cocycle on the two generators, if the group has no relations, then you're fine. You can extend the cocycle uniquely, and there are no issues. But if the group has relations, like in this case, psi s squared is equal to 1, which means that psi s squared, which is psi s plus psi s slash s, should be 0. And this is, well, in this case, it's kind of trivial because of the way it works. I mean, you just have to look at this matrix and multiply it by this vector and add them up to see that actually it kills this relation. But the other relation is psi slash ts cubed should be 0. And if you work it out, it's some non-trivial combination of these things. But, well, in a sense, it's not a non-trivial fact that it vanishes, because the fact that it vanishes is an identity in the group ring. So it has nothing to do with the properties of phi, which is good because we hope to solve it more or less for all functions. Okay, so now we come to the problem which I haven't actually said how to do. So I introduced the notion of modular integrals. I gave one example, and I said almost nothing about how to actually solve this problem. And in the remaining couple of minutes, I will briefly explain why the answer is not as hard and why it involves certain modular objects. So for my sanity, let's not look at the 6-dimensional vector valued this modular integral equation, because to be honest, I haven't worked out this particular way of approaching the problem in full generality in that case. So I will talk about how to solve this equation in the scalar case. And there is a very nice solution, which is in some sense classical, but it's very obscure, and I'm not sure if I have any good references for this. I have some results coming from different areas, which are more or less equivalent to this method. But the general idea is you can solve this equation somehow using Green's functions. And it's maybe by contrast, you could think about differential equations. So if you know very well how to solve homogeneous differential equations, there are sometimes ways of solving inhomogeneous equations using that knowledge. And something similar happens here. So there is a certain integral representation for these solutions, which involves this kernel K of tau z, which is called the modular Green's function. And so on this slide, I will explain in more general, somehow more general picture, but on the next slide, I will give a very simple kind of, I don't know, first year complex analytic idea of what's going on. So just using terms from complex analysis. So the general solution more or less looks like this. You have to find a certain kernel function in two variables, which is modular in both of the complementary weights k and 2 minus k, and which has only simple poles at the simple poles for a fixed variable. One of the two variables only has simple poles at the PSL2Z orbit of the other variable, together with the restriction that at the diagonal, the residue is actually constant, so it doesn't depend on the other variable. And there's a certain condition at the cusps you need. And let me explain now in more down-to-earth terms how to solve it for k equals 0. So for k equals 0, I will say explicitly this kernel turns out to be this function. So it's either you take the J invariant, you take its derivative and you divide by the difference, or you can, well, you can actually calculate the derivative of the J invariant, and it's this thing. And so let me now explain why this actually solves the problem. So these two conditions have the translation condition and the inversion condition. If you look at in the fundamental domain, then what you're saying is, well, the translation kind of glues together these two sides of the fundamental domain. So the translation condition tells, well, when you approach this side, and then when you approach this side, the difference between the two values should be given by this cocycle psi t at point tau. And the S relation, again, is similar, and it tells you something, but what happens when you approach the two green arcs here and here, on the darker and on the lighter side of the fundamental domain. Now there's a way to see this picture in a much cleaner, I mean, there's a way to write, to represent this picture in a much easier situation, which is, so what you do is you conformally map the two pieces of the boundary which you want to have, for which you want to have a relation to be the same piece of the boundary in some different domain. So you do it for the two green arcs and for the two red rays. And what you get, well, you get a cut plane. So there is also this kind of dashed line here, which, so you map the light like hyperbolic triangle on the left to the upper half plane and the dark hyperbolic triangle to the lower half plane. And then you choose the values of I and omega to be 0, 17, 28, and 0. And actually, you already know this conformal map because it's given by the J invariant. So you don't have to work out what is the conformal map from here to here. And now the conditions in terms, so if you change variables from tau to J, the conditions become much cleaner. It's just saying when you approach this green line on the two sides, there should be a jump, and that's given by the psi s, the function psi s from the modular integral equation. And when you approach the red line from two sides, there should be a jump which is equal to psi t. And there's actually a very classical way of solving this problem, which is due to Plimelli, who has, I think historically Sochotsky was first to found this formula. There's a formula which you might have seen in the complex analysis course. So let's like kind of forget all the details. So we're talking about the problem. You want to construct a function on the complement of a, let's say, finite interval, which is holomorphic, which grows nicely at infinity. So it actually decays, so it goes to 0. But specifically, let's say it decays like this. So it decays like 1 over z. And at the points of this interval, you want to have a jump between the values above and the below. And the jump you prescribe by some function wt, which in principle could be quite, I mean, it doesn't even necessarily have to be, I guess it has to be continuous. Okay, I don't want to go into that kind of details, but for nice enough functions wt, well, you can always formulate the problem. The question is whether you can always get a solution. But when w is nice enough, then there is actually a very simple formula which solves this problem, which is given by a Cauchy integral with open ends, so you don't close the loop. And then it's very easy to check that if you take your function f of z to be this integral, by the residue formula, well, no, this is the Sochotsky-Plimelli formula exactly that tells you that this jump is equal to wt. Sorry, I'm thinking about the case when w itself is a complex analytic function. So this is kind of elementary, but what you see is, well, if you go to the previous slide, I said this strange looking kernel k of tau z in terms of j variables is actually very easy. It's just the Cauchy kernel. And the solution that I described on the previous slide using these modular Green's functions. In this case, it just corresponds to the Zachotsky-Primelli formula. And now you have to believe me that this approach can be generalized to the vector valued case. And there are certain issues. So first of all, well, for this to work, we actually have to know what the homogeneous solutions to this vector valued cocycle equation are. And for this, one has to look again at these 6x6 matrices. But it turns out that this representation splits, I'm sorry, I'm going over time, but it will be finished very soon. So it splits into two three-dimensional representations, and you can identify both of them. And one of them actually turns out to be a symmetric square of SL2Z, which now you kind of can appreciate that I actually told you about this result of Kaneko and Nagatomo, that the solution, you know in advance it involves quasi-modular forms now, but actually they also give you the way to find the quasi-modular forms from the representation and to go back. So one can write down these solutions to this part now. And the second three-dimensional representation is a bit more complicated to describe, but it's actually easier, I think, to solve in a sense. In any case, it involves the other type of like generalized modular objects that I mentioned today, which is Eichler integrals of weight 2 Eisenstein series for gamma 2. So I gave you an example of Eichler integral of E4. Now you have to go to weight 2 Eisenstein series. And for that, you just have to take primitive ones. And it turns out that this is maybe more familiar in classical terms. So you just have to consider these two functions. So log of lambda of tau and log of 1 minus lambda of tau, where, well, unfortunately, I haven't quite mentioned anything about lambda, but it is a very famous modular invariant, modular function, which is called the modular lambda invariant. And well, I did mention what the theta function was. So if you want, you can use this formula as a definition. Okay, so I don't know, maybe I should stop here. See if there's any, if there are any questions.
Thanks very much.